Hi, welcome back to educator.com. Today we're going to have our function petting zoo. An important step in learning mathematics is becoming accustomed to how various functions behave and what their graphs look like. While long-term experience is the surest way to familiarize yourself with functions, and you've probably already got some of that experience. When you see x squared show up, you've got a sense that, oh, I'm going to see a parabola, right? This lesson is here to give you a head start on developing your function intuition. So maybe we'll see some that we haven't really talked about before. I'm actually sure that you'll see a couple that you haven't really talked about before. And you'll get the chance to sort of develop it. We'll talk about various properties, that sort of thing. So we can just get a sense of, oh, when I see functions in this type, I know to expect a graph like this. I know to expect certain kinds of behavior. So we're going to graph various fundamental functions, and we'll talk briefly about their key points. Don't worry about memorizing this information. So don't worry about memorizing this stuff. It's not here because you're going to have to know it, because you're going to be drilled on this. It's never going to be tested directly, probably. I suppose there might be a couple teachers out there who would test directly on it. But really what this is about it's about exposing you to these so that you're ready to understand things better down the road. And other teachers or books might call similar lesson a function library or parent functions. I personally think it's kind of fun to call this a function petting zoo, because really we're just going out and we're meeting a bunch of different functions. We're getting the chance to interact and play with one function, another function, just for a little bit at a time. The point of any of these names, though, is the same thing. Function library, parent functions, function petting zoo. All of these things are just to introduce or review a wide variety of fundamental functions, and then also talk about their characteristics and their graphs to get you the chance to develop that function intuition so that when you see a function, you know what to expect out of it, even if you haven't worked with that precise one before. All right. Before we get into this, though, don't forget that axes matter. Remember from our very first lesson on graphs, how the axes are set up has a huge impact on what the graph looks like. Whenever you look at a graph, pay attention to how the axes are set up. For consistency and to help us see how various functions behave differently, all the graphs we're about to see will all be on the same axes. So the graphs we're about to see are going to be on the same axes. We'll see them all on the x horizontal -10 to 10 and the vertical -10 to 10. And notice that these are square axes. The length of the horizontal is the same as the vertical length. So it's going to not give any sort of weird curving to it. We won't be squishing the picture from its sort of quote unquote natural size, its natural shape. So these axes will help us see how each one of these compares to the other one. So we'll have a general template to understand how is the shape of this one different from the shape of this one, different from the shape of this one. All right, let's get going. All right, very first one, the constant function. F of x equals k, where k is a constant. So just some constant number. So things to notice about this. So for example, in this one, we've got k is a little bit more than 3. So the input doesn't matter. No matter what we put in, right? 2 gets mapped to the same thing as 10, gets mapped to the same thing as -8. Whatever we put in, it all gets mapped to k. Output is thus always the same. So output is always the same. Whatever we're putting in, once again, it doesn't matter what we put in, it always gives the same thing out. And then finally, what does it put out? It always outputs a horizontal line at k. So we plug in 5, it spits out k. We plug in 20, it spits out k. We plug in -47, it spits out k. So when we look at all of that together, graphically we're seeing a horizontal line at height k. Great. The identity function, f of x equals x. It's called the identity function because whatever we plug in is what we get out of it. The input is the same as output. So input is the same as the output, right? If we plug in 7, we get out 7. If we plug in -47, we get out -47. So what we get out of this is we get this nice straight line that just cuts perfectly between the x-axis and the y-axis. We see a slope of m equals 1 because of this. So slope equals 1. We get slope equals 1 because it has to cut evenly between them, otherwise it wouldn't be giving an identity, where the same thing that goes in, if 6 goes in, then 6 has to come out, right? So whatever goes in is what comes out. All right, that's the identity function. The square function, f of x equals x squared. So first thing to notice is that as it goes to the right, notice how it starts to go up faster and faster. And as it goes to the left, it goes up faster and faster. So the height increase, how fast it's going up, its rate of change, height increase speeds up farther out. The farther we get away from the middle, the faster it's moving up. So height increase is speeding up farther out. The other important thing to point out is that on the right we're going up and the left we're going up. So on the squared function, the ends go in the same direction. So ends of graph go in same direction. They point in the same direction. So this is an important idea about the square function, is that we can trust the fact that it will cup in the same direction. The right side goes off in the same way as the left side. This cube function. So the cube function, similar to the square function, its height increase speeds up the farther we get out. So the height increase speeds up as we go out. In fact, its height increase is going to speed up even faster. When we get to 2 on x squared, we're only at an output of 4. But when we get to 2 on x cubed, we're at an output of 8, right? 2 times 2 times 2. So its height increase speeds up, and it speeds up even faster than it does on x squared. The other thing to notice is that if we were to continue the graph, one side goes up and the other side goes down. The ends of the graph point in opposite directions. So unlike x squared, where they point in the same direction, the ends of the graph in x cubed, ends of graph point in opposite directions. So the ends of the graph, when we're doing the cube function, will point one way up, one way down. So opposite directions. Great. All right, next one, the square root function. For the square root function, notice the farther we go out, the slower it's increasing in height, right? To get to a 2 of height, it has to put in a 4. To get to a 3 in height, it has to put in a 9. To get to a 4 in height, it has to put in a 16. So height increase slows down as the farther we get out. So height increase slows down. Also, notice the fact there's nothing over here, right? There's nothing on the left side of the graph, because if we try to plug in a negative number, it's not in the domain. So negatives are not in domain. So in a way, square root of x only looks like half of the thing because it doesn't really keep going. Part of it just stops because if we try to plug in negative numbers, square root fails to work, right? Square root, there's no number that you can square it. There's no real number, at least, that you can square that will make a negative number. Negative number squared gives you a positive number. Positive number squared gives you a positive number. So there's no number that you can square that will give you a negative number, at least in the real numbers. So the negatives are not in the domain of the square root function. The reciprocal function, 1 over x, called the reciprocal because the reciprocal of a number is just 1 over that number. So in this one, height increase as we get farther and farther out, height increase slows down, right? Height increase slows down when we are far, so when we slows down away from the y-axis. The farther we get from the y-axis, the slower the height increase becomes. However, right, and this makes sense because at 2 we're at 1/2, at 4 we're at 1/4, at 6 we're at 1/6. So the height increase, well, I guess decrease, it's increase as we go to the left, but the point is the change in the height. Height change, I'll change that formally. Height change slows down away from the y-axis. But as we get close to the y-axis, as we get closer and closer, height will blow out, right? The height is going to blow out. So near 0, the function blows out. And by that I mean it blows out to either positive or negative infinity, right? As we get to 0, as we approach 0 from the right side, we blow out to positive infinity. As we approach from the left side, we blow out to negative infinity. However, there is one point that simply isn't allowed. 0 is not in domain. Why? Because 1 over 0 would be not allowed, right? We're not allowed to take dividing by 0. So 0 is not in domain. We can talk about what happens to 0.00000001, but we can't talk about what happens to 0 itself. So 0 is not in the domain, but near 0, as we approach 0, it blows out to either positive or negative infinity. We'll talk about this more when we talk about asymptotes, vertical asymptotes. All right, spelled kind of weird, just in case you're curious to look at it right now, asymptotes. Weird spelling, but pronounced asymptotes. All right, next one, absolute value function. For this one, it's only going to output positives, so only outputs positives. Why? Because absolute value only spits out positive numbers, right? If you put in -3, it becomes +3. You put in +3, it becomes +3. Whatever you put in, it is stripped of negative numbers. It has to come out as a positive number. Notice that it's also kind of similar to f of x equals x, right? When we've got that normal f of x equals x, it would keep going like this. So that's the thing to notice, is that in a way, it flips its direction upon touching the x-axis, the x-axis. So it flips direction when touching, upon touching, I'll make it exactly correct. So upon touching the x-axis, it flips the direction that it's going. And what I mean by that, let's imagine that we start over here at -10. We'd get +10, right? And we're moving this way. We now plug in -8. We get +8. We plug in -4. We get +4. We're going this way. We're going this way. We're going this way. We're going this way. All of a sudden, we hit 0. We hit a height of 0, and it bounces up. It flips to going this way right here. And this is because it only outputs positives. So when we would get below the x-axis, it has to bounce off, because otherwise we'd be outputting a negative. So it flips the direction that it's going in upon touching the x-axis. All right. Now the trigonometric functions. These ones, there's a good chance you haven't seen these, or if you have, they're pretty new to you at this point. The trigonometric functions, you'll learn a lot about these in trigonometry, but right now the main thing I want to point out is the fact that they repeat, right? Sine of x just does the same thing, right? See, this interval here is the same as this interval here, is the same as if this chunk here is the same as this chunk here. We're just seeing it repeat. Cosine of x, this chunk to this chunk, is the same as this chunk to this chunk. We're just seeing it repeat. They're slightly different in how they're set up, but they're repeating functions. Let's also look at it in a different axes so that we can understand what's going on better. This is the classic -10 to 10 axes that we did for everything else, but how about some other ones? It turns out that it does its variance between 0 and 2 pi. Don't worry about actually getting what's going on here. I just want to have you see this stuff so it's not totally new when you see it later. You'll get it all very well in trigonometry. From 0 to 2 pi, we've got one repetition. From -2 pi to 0, we've got another repetition. It repeats itself every 2 pi. It also varies between 1 and -1, both for sine and cosine. Varies between 1 and -1, and it also has repetitions on a 2 pi basis, both for cosine and sine. We'll see why this is the case when we actually study trigonometry, but the main thing to get out of this right now is that trigonometric functions are these repeating functions, that they're a way of being able to see the same thing happen after we go down far enough. We go down a certain amount, and it becomes the same thing. Go down a certain amount, it becomes the same thing. They repeat themselves. Exponential and logarithmic functions. All right, we're back to our -10 to 10, our standard axes that we were used to before. Thing to notice here, on exponential, it blows out really fast. So it blows out, look at how fast this manages to go out of our axis windows, right? We get outside of being able to see this out of our viewing window so quickly. By the time we've made it to 1, we're at 10. At 2, we're at 100. At 3, we're at 1,000, right? So exponential functions, this is 10 to the x is only one possible exponential function, but they're going to blow out really, really quickly. They're going to just shoot up, absolutely massive height. Blowing out probably isn't the perfect word since we used blowing out for asymptotes. Let's instead say its height grows really fast. So height grows really fast. Over here at log 10 of x, look at how long it takes to even get up to 1. It takes us out to 10 to get it. And we can see that the height is slowing down. Its increase in height slows down. So its height increase slows massively. So it grows really, really slowly. That's probably the main important things to get out of these. Don't worry about actually understanding what's going on precisely right now. We'll have an entire section on this when we talk about exponential and logarithmic functions in detail for an entire section. But right now I just want you to go, oh, exponential functions get really big really fast, and logarithmic functions stay pretty low for a very long time. Just to make a point of how long these sorts of things are, how slow and how fast they are for logarithmic and exponential respectively. Let's look at it with new axes. So for our exponential, we're going from only -3 to 3. By the time we've made it out to 3, we've hit 1,000. 1,000 is how big we've managed to get. And it doesn't actually get to 0, it just looks like that. It's approaching it, because -3, 10 to the -3 would be 1 over 10 to the third, 1 over 1,000. So it's just really close to the 0 axis. Once again, don't worry about understanding this perfectly right now. We'll talk about it later. Logarithmic functions, they're going to take forever to even get to reasonable numbers, right? We have to get to 1,000 before we even manage to make it up to a height of 3. So they grow really, really slowly. So the height growth on logarithmic functions really, really slow and slows down massively the farther you get out, whereas exponential functions really, really fast and increases massively the farther you get out. All right. So, of course, the functions we see, that makes it for our petting zoo. We've completed our petting zoo. But when we see functions out in the wild, they're normally not going to wind up being in their pure form, right? They're not going to be x squared or square root of x. Normally, they've had other stuff put on them, added on them. They've been shifted, stretched, or flipped. They've been transformed in some way. Still, it helps to know the general shape for a function before transformation. Beyond these shiftings, stretchings, and flippings, we can still have a pretty good idea of what's going on. Other times, functions will be mixed with other functions. We might have things like f of x equals x cubed plus x squared, right? That's not just one pure function, that's x cubed and x squared. Or x squared times the square root of x. Once again, that's not just one pure function, it's two functions mixed together. Or h of x equals the absolute value of x cubed. Once again, not just one pure function, it's two things put together. It's absolute value and x cubed. Once again, though, it helps to know each function's general form before trying to figure out how they interact. If we understand how absolute value of x works and we understand how x cubed works, it will make sense to us when we work on the graph of the absolute value of x cubed. We'll have a better understanding of what's going on, what we're seeing. We'll learn about both of the above ideas in the lesson's transformations of functions. The transformations where we shift, stretch, and flip will be in the transformations of functions lesson. And we will talk about composite functions. We'll talk about arithmetic combinations. These first two are arithmetic combinations. Once again, don't worry if you don't know what these things mean precisely. We've got lessons for that. And then finally, an actual composite function where we've combined the way that two functions are working. So we'll learn about these in much greater detail in those two respective sections. All right, great. Ready for some examples. Here are two graphs without axes. They are the graphs of what functions? Well, this one, it's going up. It looks like a slope of 1. It's pretty stable. It's just increasing continuously. It doesn't bounce. So this is almost certainly f of x equals x. Great. And this one, one side goes up. We see this sort of blowing out, right? It's approaching negative infinity is what it's blowing down to here, and it's going up to positive infinity up here. So what blew out and what got sort of really, really slow in its height change? Oh yeah, the reciprocal function, f of x equals 1 over x. Great. Next, here's two functions that have been shifted, stretched, and or flipped. What are the base functions making them up? So for this first one, the red graph, we think, oh, well, it looks kind of like a parabolic arc, but a parabolic arc on its side, well, it's parabola. Oh, hey, look, over here, there's nothing over on the left side. So if there's nothing on the left side, it's cut out the negative side. It's cut out the left side. What cut out one side? Square root of x. We've got that square root of x, and its height increase, so height increase is still slowing. So height increase slows the farther it gets out. So that's both of the identifying marks of being a square root of x function. It's very different than the normal square root of x, but the basic function that's making this up is root x. It's been shifted, it's been stretched, but it's still root x. What about this one over here? Well, hey, it's going down, so down on both sides, and its height increase gets faster. So height increase Well, height increase is incorrect. It's not a height increase because we're going down, but it is a height change. And that's the more fundamental idea about x squared. Isn't necessarily that it has to be going up, but that the change, the rate that it's going up, or the rate that it's going down possibly, is continuing to increase. So height change speeds up. The farther we get out from the center has been moved in this one, the height change will speed up. We get faster and faster changes in our height. So once again, this is f of x equals x squared. It's been shifted, it's been flipped, and it's been stretched, but we can still recognize, hey, that's a parabola. It must be at heart coming from that same idea as behind x squared. Great. Example 3, we want to graph f of x equals x cubed, g of x equals x squared, and h of x equals x, all on the same axes. And we also want to set up the axes such that we go from -10 to 10 on the horizontal, and none of the graphs are cut off vertically. So that means we can't lose any vertical information. So to help us understand what's going on here, let's make a table. Now we know what x cubed looks like, what x squared looks like, and what x looks like in general. So we can use that information to help us out. So let's see what the extreme values are and what the middle values are. So here's our table, x, f of x. So here's x at -10, x at +10. So f of x, let's make all three of them. So x cubed, x squared, and x. Let's actually use colors for these. So x squared will be in red, and blue will be x. Great. So if we plug in -10, we're going to get -10 cubed, which is -1000. X squared will become 100 positive because the negatives cancel out, and x will become -10. If we go to the other extreme at 10, will that be at +1000? X squared will also be at +100, and x will be at +10. So let's try some other things. Let's look at what happens in the middle. Well, in the middle, x cubed's at 0, x squared's at 0, and x is also at 0. Let's see what happens in the middle between the middles. If we plug in, say, 5, we plug in -5 and 5. -5 times -5 is +25 times another -5, we get -125. Over here we'll have +125. The reds in this will get squaring, so we'll be at +25, +25. And we'll have -5 and +5. And finally, at 1 and -1, -1 will go to -1, +1 will go to +1 for x cubed. For x squared, -1 will get it canceled to a positive still for the positive, and then -1 and +1. So the thing to notice here is that when it's close to 0, they're not that different, but the farther we get from 0, the more their differences become apparent. So let's make our graph. We'll do it in blue, which hopefully won't be too confusing, even though blue is connected to x. So what is the maximum vertical height that we have to have? The maximum vertical height that we have to have is a whopping 1,000, because we get up to -1,000 and +1,000. So we have to be at -1,000 and +1,000 as the vertical extremes. So here's the middle at -500, +500, and then we'll actually tick off. We'll go to an extreme of 10 and -10 horizontally because that's what we were told to do. And here's our middle at 5 and middle at -5. And here is 1 and +1. Great. All right, so at this point, let's graph x cubed. This is probably the one that'll be easiest to graph. At 0, it's at 0. At 1, it manages to be up 1, so it barely hasn't even got off the x-axis. At 5, it's at 125, so it's a little bit over a fifth of the way to the 500. So let's say it's around there. And then 10 is going to be all the way up at 1,000. -1 to -1, barely off of the x-axis. -5 will be at -125, so we're a little past, close to it's probably a little too far down, actually. We're about a little over a fifth of the way to the 500. And then finally, at -10, we're all the way at a whopping -1,000. So its curve is going to look like this. Right? It manages to grow massively, very, very quickly as it gets farther and farther away from the y-axis, as it gets farther and farther from the center of its graph. What about x squared? x squared, we get 1 and 1, same location. 5, and it's at a 25, a meager, tiny jump above. And then at 10, it's at 100, so it's a little bit below the height of x cubed at 5. Same on the reverse side. So the parabola, when we look at it this far out, it's growing fast. You know, it manages to get to 100 by the time it's gotten to 10, but it's still tiny, tiny. It looks so stout, right? It looks so short compared to x cubed. Finally, we look at what happens to x, just the plain old identity function, and at 10, it manages to only be 10 above. So we're talking like there, negative 10, it's only negative 10. So we've got like barely growing off of that x-axis. It's barely breaking away when compared to these giants like x squared and x cubed. So when we're really close to actually being near 0, when we're really close to the center of these graphs, they're very similar. But when we look at them on a larger scale, and not even that big, just negative 10 to 10, suddenly the differences become apparent. They become massive, huge differences. The difference between x cubed and x squared at just 10 out is a difference of 900. Huge differences between these, and they get even bigger the farther we go out. Final example, example 4. Think about functions of the form f of x equals xn, where n is a positive integer. It's contained in the natural numbers. We distinguish the difference between when n is odd and when n is even. So let's look at some examples for when n is odd. So n is odd would be like x, or maybe x cubed, or x to the 5th. So x, we know what x looks like. It's just just like that. X cubed, it blows out pretty quickly. X to the 5th, it blows out even faster, right? By the time it makes it to 2, it's at 2, 4, 8, 16, 32 height. So by the time x to the 5th has an input of 2, it's getting an output of 32. So it blows out really fast. Really fast. Let's compare some even ones. Say we've got x squared. Well, we know what that one looks like. Just looks like a parabola. X to the 4th. Well, like a parabola, but it grows even faster, right? By the time we get to positive 2, instead of just being at 4, we're at 16. So it grows really fast. Not quite as fast as x to the 5th, but faster than x cubed. And as we go to the other side, since negative 2 squared is positive 4, negative 2 to the 4th is positive 4 times positive 4, or positive 16. So as long as we're even, we're going to cancel out those negatives. And that's the idea that we see right here. So look, when we're even, we go off in the same direction. If we were to do this for x to the 6th, it'd be the same thing, but growing even faster. We'd just be growing even faster. So what we're seeing here is when n is odd, so n odd means that the ends of graph go in opposite directions. So the ends of the graph go opposite directions if n is odd. But if n is even, the ends go in same direction. So that's the major difference between these. In many ways, they're very similar, right? The higher the n, the faster we've got this growth rate. But depending on if we're odd or if we're even, changes whether or not the two ends will point in the same direction. If it's even, they're both pointing up, as long as there isn't a negative in front. And if it's odd, one of them is going to be pointing down. The first one's going to be pointing down as long as there's not a negative in front, because a negative raised to an odd number remains a negative. So n is odd. If n is odd, we have opposite directions. If n is even, we have same direction. All right, great. So that finishes up for the examples. I hope you've got a good idea of the various functions out there. There's a lot of functions out there, but at this point, you probably got a reasonable understanding of what they're going, and just the more you continue to do math, functions are just going to make more and more sense. Just pay attention to what you're doing and go, oh yeah, I've seen this guy before, or oh, I haven't seen this guy before. Pay attention to what he looks like, and then the next time you see something like that one, you'll be able to apply that information and have a better idea of how to draw that curve. All right, we'll see you at educator.com later. Bye.